PhDs, which are going to present their work and results to all of you, and we have also a regular lecture by Professor Palunko at the end. So the first one to break the ice is Rogić, who is a PhD student from August, and so Frane, the floor is yours.
Hello. Hello, I'm Frane, and I'm here to talk about underwater localization, about some problems that we encountered trying to solve this problem, some of our ideas, and some solutions that we found were appropriate for certain situations. So the introduction, in underwater localization, we don't have access to the global navigation system, as GPS signal or Wi-Fi for that matter don't propagate underwater. And as we need to have the location of a robot to achieve most tasks, it's a necessity to find a way to do it. The easiest way to get a location of a robot is to have some sensors like IMO-DLL, and using that reckoning to calculate their positioning. But the problem with this approach is that they have a cumulative error, which means that every time we have a wrong measurement, the error just increases and increases, and we have no active way of reducing the error in positioning. So the solution to this is to add another measurement, with range measurement from a known position, and then we can actively reduce the measurement and bind it to a sphere if we don't have a depth measurement, or to a circle if we do. So this is the AOE model that I used in the simulations I'm going to show later. It's a unicycle model that has no sway motion. That means it's underactuated. This was picked because it can estimate diver motion as well. And it's a quite simple model that's often used. The main problem with this kind of model is that you need to estimate the currents very efficiently. Otherwise, in real life situations, you can have big issues where your filter will diverge. So to achieve underwater ranging, you need an acoustic nanomodem because you have no other way of communicating. So this is one of those modems right here. You can send data messages, range messages, or you just ping with it. The main problem with this kind of communication is the time necessary to receive one measurement, because you need to add up all these times, and then also as the sound speed is only 1500 meters, you need to also add that into consideration, and basically the frequency at which we can get measurements, range measurements, turns out to be around 1 hertz, which is quite low for today's standards. So then, because the frequency is so low, we need to ensure that every measurement that we get is observable. Observable basically means that every time you get a measurement, you can reconstruct a state vector from it. So in that state vector, you have position, pose plus speeds. So it turns out that this is the observability matrix. As you can see, it has two speeds right here. The first is the speed of the vehicle, and the second is the speed of the beacon from which we range. As in most cases, the beacon is static, we need to ensure the vehicle is in constant motion to ensure that we have binary observability. And even this is not enough, because the frequency of the ranges is so low, we need to ensure that we always have the most informative range. And this is done by calculating Fisher information matrix, and from it you can get this constant here. And this constant basically, inverse of this constant tells us just how informative our measurement is. And this constant depends on range from the range of the vehicle from beacon speed and this angle here. This angle you get by this angle is between two vectors. The first vector is the vector of the direction of the vehicle, and the second vector you get by between two dots, the vehicle and the beacon. And we did this observability problem for CoMe2 trials. We had a racetrack-like trajectory, and we got these results. It turns out that perpendicular positioning of the beacon. So every pixel here is the beacon position, and this racetrack here is the trajectory of the vehicle. So it turns out these perpendicular positions are the best, while in the middle is still okay. And this is expected as we have a sinus here, and we get maximum informations when we get when it's perpendicular, right? And this is very important, as you can see in the trajectory itself, you get the worst results if you place a beacon on the trajectory of the vehicle. So what we did next is we took a robot localization package, and the robot localization package provides nonlinear state estimation through fusion of different sensors, and it has a lot of sensors. It has E-model, pressure sensor, magnetometer, etc. But it did not have range. It did not accept range measurement. And this was quite important to us because during the last break in the service, we noticed that this vehicle here, UNIZG, that had this package, after extended periods of time underwater, the error it created was quite large. And as it does a sensitive task like interacting with robots, we needed to find its error to a certain degree. So what I did is I already had a MATLAB ECHO filter, and we modified that robot localization. So we created a path with different measurements. We did not calibrate any parameters in either filter, so in this picture they're different. That's why odometry, MATLAB odometry is different than the robot localization package. But we can see that both the results with ranges are much better than the ones without. So beacon in this simulation was in 100 position. So what I did next is I calibrated all the parameters to be the same, and I let them run I drew a hexagon kind path, placed the beacon in the middle as that was perpendicular to the sides of the hexagon, and that created a very good observability. And I let them run a couple of circles to see what the end result was going to be. So I knew that, well, of course, the range measurements should be much better than the ones without it, as the noise that we put into the measurements of speed and acceleration were quite large. So these were the final results. We can see that the results with range measurements are very good, and they're very close to the true pose, which is blue, while odometry keeps increasing very, very fast. And after a certain period of time, you can basically do nothing with these because they're almost 20 or 30 meters away from the true pose. So this is a graph. This is the number of iterations we had in MATLAB, and this is a distance from the true position. As we can see that very fast, the odometry without range, the error increases while it's almost linear, and at the end it should not pass a certain threshold because it needs to be on a circle. because we create a circle with our range, and we bind the error to that circle. So what we did next is a so-called breadcrumb localization. So the idea of breadcrumb localization is that the AOV will place its own beacons. And these beacons will have uncertain positions because AOV will, of course, have some kind of error when it places its beacons. So this kind of approach will result in problems with observability even higher than before. Because on the trajectory itself, the observability is the lowest until it turns. And then the angle changes and we get problems. But in this way, we can increase the range that ROV can move. It's a very fast solution. You don't need visual odometry. You don't need a lot of time. It's very easy calculations, and still you can get really good results with it. Especially if you have a pre-planned path, like I did here. You can place the beacons in certain locations right before turns, and that way you ensure very fine observability, and the error never passes a certain threshold. Main problem, also one of the problems with this approach is acoustic interference, which means you cannot let two beacons talk at the same time. So you always have one range, but you can always pick which range you want to talk, and you always pick the one with most observability at any given moment. And as you're going to see here, right at the end, we have a slight drift because this observability was not that great. You're going to have a slight drift, but when the beacon comes back down, as is intention with this breadcrumb algorithm, it binds the error right back on the track because X observability is much better. And this is the intended solution, because on the way back, we can use old beacon positions to ensure that the AOV returns straight to the location. And you can see that right here. At the end, it drifted apart, but then when it came here, around here, into the range of this beacon, which had very fine positioning, very fine observability, it bound the error right back on the track. So I also forgot to mention, but when it leaves the site of the beacon, it pretends that it cannot access that beacon, of course. Yeah, thank you. That was it.
Thank you, Fran. We have for questions.
Hi, so thanks for the presentation, very good introduction to the AKF. I have a couple of questions, first of all, regarding the motion model that you're using. So I saw a constant velocity model, I think.
Yeah.
Okay, so which kind of trick or different model are you using for the turns when the robot turns to another direction? Are you resetting the uncertainty of the model, or?
No. This kind of model, basically we have a propeller in the back, right? And a steering wheel here, so we can turn. I don't reset the error. If you mean covariance matrix, or?
Yeah, sure. So you have like a model of how the robot is turning, no?
Yeah.
In this matrix. So
Yeah. No, I don't reset the covariance matrix if that's what you're asking, because I want to have the angles as well, right? If I would reset the covariance matrix, it would just increase the uncertainty, and I would not accomplish anything.
Okay, but you're not using constant angular velocity, no? Or yes?
No, it's not constant. No, it's in the moment, right? When you need to turn, I can turn.
Sure. And the second question, how are you dealing with the reflections of the acoustic measurements?
You have a notice threshold, right? And if it's over a certain limit, we just refuse the measurement. It happens, I think, 10% of the time when we did the testing on our acoustic models.
So in the case, in the last experiment that you were showing, the black things were like walls?
Yeah, walls.
So in that case, there comes a time when you don't
Yes. They're bouncing in the walls, right, sound waves, and we refuse those measurements because using our API position, and we know the beacon position, right? We know approximately how long the range should be, and if it's over a certain limit, we just say, no, that's acoustic error.
Good, thanks.
Any more questions? Okay, Okay, our next speaker is Babić. Ana is a researcher and PhD student from University of Zagreb, from Labus Laboratory, and Ana worked on several research projects in Labus, CADI, Labus, subCULTron. Ana's research interests include evolutionary, neural and bio-inspired robotics. And I believe that Ana is now at the end of her PhD, and she's going to present her work on achieving long-term autonomy in heterogeneous swarms of marine robots.
Thank you for the introduction, Tamara. This title is quite a mouthful. This is the title of my PhD. The title is A Hyper-heuristic Approach to Achieving Long-Term Autonomy in a Heterogeneous Swarm of Marine Robots. I hope to explain each part of it to you today. First, however, I would like to give a bit of a context to this research. Tamara mentioned this project, subCULTron. I'm certain a lot of you are familiar with it. This is, let me just show you that. Okay. The subCULTron project arose as a means of addressing a problem. So there is this very challenging, very specific environment of Venice in Italy, the lagoon of Venice. It has a set of very specific phenomena that occur and that the researchers there wish to study. However, studying this environment means that people have to go out on boats. It's a lot of very costly procedures, deploying, collecting probes, etc. So the idea was that a swarm of robots could do this work instead of these people and boats and etc. The subCULTron swarm was envisioned as a multi-layer robot swarm. There are three kinds of agents inside it. We have on the surface A-pads, which are floating artificial lily pads, so to speak. We have the maneuverable A-fish in the middle layer of the system, and we have the aMussels, or artificial muscles, which are the main center of the system, and which are mostly collecting data at the bottom of the sea. I will primarily talk about the A-pads and aMussels within the context of this presentation. So here we see an example of these agents. First, the aMussels. So the aMussels are significant because they are by far the largest part of the swarm. There's over 100 units. They are very limited in their movement capabilities. They only have a buoyancy system, which allows them to float up to the surface or sink to the bottom. For any other movement, they require the assistance of the A-pads. Significantly, they have many sensors, and the goal, of course, is for them to collect as much data as possible and for the APADs to redeploy them to certain locations which would be of interest to detect anomalies or simply provide monitoring on a long time scale. For this long time scale aspect of their functioning, they have rechargeable batteries and they have inductive charging coils, which enables them to be recharged on the fly during the mission. The APAD is greatly outnumbered by the aMussels. As we see, there's only 5 of them in the swarm. They are overactuated autonomous surface vehicles, and they act as access nodes for this underwater network that the aMussels represent. Each APAD has 4 of these docking stations with which it can dock aMussels and charge them in parallel or simply transport them elsewhere. This is the monitoring scenario, which I will go over now. So there's a large number of aMussels performing an environmental monitoring mission. They are for most of the time they are underwater. Sometimes they float up to the surface. This is why they have several modes of communication depending on the environment. The APADs, while this monitoring is taking place, the APADs are patrolling on the surface, and they, among themselves, make a sort of patrol agreement on which aMussels are the responsibility of which APAD. After this is done, each of the APADs then proceeds to schedule and sequence pickups and charging of the aMussels and conducts this decision making. And of course, after the decisions have been made, the APADs implement execute these missions. I would like to focus on this last part, which includes this hyper-heuristic algorithm for the mission planning and decision making. So this is a structure which seems complex, but it's not really. The main idea here is that we have So we have the actual problem domain. So this is the specific situation we are dealing with. So we are dealing with vehicles in a marine environment. We're dealing with motion, movement costs, energy sharing, etc. While this entire section of the algorithm is completely abstract. So the hyper-heuristics is essentially a heuristic which chooses heuristics, meaning that we have a set of low-level heuristics, which means methods for scheduling or sequencing and decision-making. We have a way of scoring them and observing their performance, and we have another heuristic, which then uses this abstract data to choose which heuristic to apply in the next steps. To start with, briefly, which heuristics have been developed for this swarm. So these are very problem-specific heuristics that have been chosen based on some particular situations the swarm needs to deal with. So we have the cautious heuristic, which means the APAD focuses on aMussels which are most in need of charging. We have the greedy method, which means the APAD focuses on minimizing its own movement. We have random, which is a purely stochastic element. It's self-explanatory. We have rescue, in which an APAD tries to collect aMussels which are furthest from the center of this cluster of aMussels to prevent aMussels from potentially being lost or something like that. And we have rush, which is a method in which the APAD focuses on aMussels which are in need of charging but are still quite okay with regards to battery state, so it doesn't, so to speak, waste time on charging. Now, the scoring of these low-level heuristics means that we have to focus on actual parameters that imply something for the success of our goal, which is the long-term monitoring mission. So here we have 4 performance indices for these low-level heuristics. We have how many aMussels are active at a certain time. We want this to be as good as possible. We want to minimize the movement cost of the APAD. We want to maximize the area the aMussels are covering, and we want to maximize the aMussel uptime, which is a measure that measures how much useful work the aMussels have done within the span of a mission. Because significantly, while aMussels are charging, they cannot perform useful work because most of their sensors are on their top cap. For charging, they have to emerge and be on the surface. So we have to balance the time spent charging, which will prolong ultimately the aMussels' ability to perform work, but also this is a certain a sort of wasted time, so to speak. The scoring here is based on a simple historical average. So after every application of a heuristic, while this mission is happening, it gets scored on these performance indices which I just mentioned. And compared to the historical average, if the heuristic has performed better, it will be scored well. If it has performed worse, it will consider to have failed. After this, we jump with this domain barrier, and we are now in the purely abstract hyperheuristic space, which means that all of this scoring now becomes a statistical tool for the heuristic to observe the past performance of all these low-level methods it chooses between. So the selection here is a relative selection, and what happens is, based on the recorded performances of the heuristics, their fitness is adjusted, meaning that if a method has performed well in the past, it will have a greater chance of being chosen and applied in the future. Finally, very briefly, acceptance criteria right now, this is very simple. If a solution that an APAC has produced is viable, it will be implemented, but this will in fact be replaced with a simulated and algorithm in the future. And now very briefly, I would like to give an overview of the experiments. One specific factor here is that obviously experiments with a swarm of 100 agents are very logistically challenging or practically impossible. The long-term element of it is also very challenging. So the motivation here was to develop a sort of semi-simulated vehicle-in-the-loop method of testing all these potential behaviors and interactions of agents. So in fact, we have this structure where an APAC platform is real and has all this developed software and firmware, etc., that it requires for functioning. And we have a surface station which has simulated aMussel agents. This segment contains a lot of other work which I will not go into in detail here. We have modeling of aMussel batteries to have, based on experiments with real aMussels, to have as realistic a simulated aMussel as possible with regards to energy sharing. We have an APAD high-level mission planning API for sort of an end-user approach to creating APAD missions. And of course, we have a mission replay and analysis screens to see what has in fact occurred during this long-term mission. And in case there are actual real aMussels in the experiments, which can also be achieved because simulated and real agents are interchangeable because of the way the communication was structured in the system, we have the ability of the APADs to autonomously dock aMussels in real conditions. Most of the experiments here, in fact, all the ones I will show here were done right here in Beograd. You can see, or you will see, the familiar pool and the beach, the bay next to it. This was one of the initial experiments. We have a simple task test of two APADs working in tandem and deciding on which aMussels are whose responsibility. This was mostly a communication and basic algorithm test. More in detail, I would like to talk about the actual proof of concept of a monitoring scenario in which we have these generated simulated aMussels that an APAD was collecting and charging them in the interest of prolonging their actual operation time. This is the experimental setup. We have the pool as well as the bay. So we had 12 or 24 aMussels in each experiment, depending purely on the spatial constraints because the pool was a bit small. The simulated aMussels weren't drifting around. They were drifting with a very small simulated drift. Their battery levels were generated randomly from an interval to make sure they're not completely depleted at the moment of deployment. And all of these positions and battery states were saved, and all the experiments were done many times. Finally, there was the surface station, which actually basically played the role of the aMussels to the APAD in the actual sea, communicating with using this very powerful antenna here. Then after a mission is done, we can observe this replay. So we have the actual trajectory of the aPad, we have all the aMussel positions, we have the battery states of the aMussels, how they, we can see which ones are charging, which ones are depleting, and here we have we are keeping track of the uptime of the aMussels. So if they are actually being charged or if their battery is depleted, they are not contributing to the work. It is this way. These are two selection heuristics that I'm showing here that were used in this particular experiment. Then, of course, we have an overview of their actual some of their performance results. We can see again these two specific heuristics were chosen because they have very contrasting behaviors. One focuses only on battery levels, the other focuses purely on position. So we have one performing as expected much better in the area of making sure the aMussels are better capable of the long-term work, while the other minimized the effort of the aPad. To also provide a sort of frame of reference, we have a baseline case where simply knowing that no charging happened in the system. And we can see we have all the aMussels working. They're of course not wasting time, so to speak, being charged, but at the end they all deplete. So this is not a very useful situation. And I have an example where actual selection took place. This is very much sped up because this was an experiment of 12 hours. Here we have the roulette wheel showing which of the heuristics is currently the most successful. And again, we have 24 aMussels being tracked, and this is the scoring, full scoring based on those 4 performance indices I mentioned before. And in the end, we saw in this particular run of the experiment that the greedy heuristic performed very well, or at least was the most popular in this instance. Finally, it's just a brief overview of a way of observing the results of all these behaviors. So we have an experiment where the one I just showed, where a roulette selection was used. We have another baseline no charging situation, and we have one experiment run for each of the low-level heuristics where only they were applied. So the system only used greedy or the random or each of them. And we can see that these are the 4 performance indices. So we have score based on how many aMussels were active. We have amount and movement cost, which we want to keep as low as possible. We have the area coverage of the aMussels, and we have the uptime score of the aMussels performing useful work. Here we can recognize some of the implications of why the heuristics were chosen in the first place for specific situations. So we have the rescue heuristic, which takes care to make sure that the coverage of the swarm is maintained, in fact maintaining coverage. We have the greedy heuristic, which minimizes the aPad's movement, keeping the movement cost low, etc. However, we see that the roulette wheel selection keeps in the middle, sort of in between, in all 4 of the performance indices, implying that it, in fact, combines bad and good sides of all the heuristics as appropriate. But of course, the actual interactions and analysis and differences between these methods I still need to be properly statistically analyzed. So this is just a rundown of some future work, which includes these rapid prototyping sorts of experiments, more rounds of these simulations with aMussels that are not in fact need to be actual agents. Then, so we can study on a bigger data set the various parameters changes, the acceptance criteria, selection criteria changes, which will, and how they actually impact the actual performance of the entire swarm and the longevity of its ability to perform long missions. That's it for me. I'm open for questions. Thank you.
Okay, we have time for one question, maybe 2. Okay, I will ask a question. So in your approach, the idea is for aPads to kind of to share their knowledge on the best heuristics. So the idea is for them to also kind of share. It's not like the API itself is optimizing the procedure.
Yes, each API itself, so in the initial step, which I didn't go into detail here, when the APIs decide they decide their control areas, etc., they communicate and they do so. There is a localization step here with an evolutionary algorithm, and then they exchange exchange their results and their criteria, and then the best result of these is chosen. So for the initial control step. After that, they are mostly independent. But the thing is that for example, the selection, the fitness wheel, etc. This is something that can be pre-trained, or so in a blank slate. So to start, this fitness of all the heuristics will be equal. But if one API requires, or if there's a pre-trained session or something like that, this can be modified to fit a certain situation, and this can of course be shared between APIs.
Okay, thank you. I have more questions. Okay, thank you. I have once more.
Thank you.
Okay, our next speaker, I can introduce him, is Marko Križmančić. Marko is a PhD student from University of Zagreb, from Robotics laboratory. Marko joined Robotics recently, 1 or 2 years ago, but so far he worked on several projects, BTS competition, and Iron project also. His advisor is Professor Bogdan, here present, and today Marko is going to present his work on consensus-based connectivity control in multi-node systems. But Marko did also experiments on marine systems, so it's kind of one between the two areas. So Marko, what is yours?
So thank you, Tamara. So okay. So thank you, Tamara, for the introduction. Yeah, so let's imagine a large underwater sensor network for monitoring simulations, like the one used in the subCULTron project. So Anya told you more about it, so I won't go into too many details. But what I'm interested in is how to achieve a strongly connected network, so the measured values converge faster. But that also means there is a potential for higher energy consumption and possible delays in messages. We also need to consider the distance between agents while maximizing connectivity. So how do we optimize the number and position of the communication links? And also, since this is an isolated system, how do we do it in a distributed way? We can start with modeling this with graph theory. So a graph G consists of a set of vertices V and set of edges that connect those vertices. It can be undirected, which means basically nodes communicate in two ways, or directed, which models on one-way communication. We say that node J is a neighbor of node I if there is an edge connecting them. And then the neighborhood is a set of all neighbors of one node. Finally, the degree of the node is the number of elements in this set. If there is a path existing between any of the nodes in the graph, then we say that it's a connected graph. Mathematically, graphs can be modeled using various matrices. The most important one, I would say, is the adjacency matrix, which tells us the weights of the links between any pair of the nodes in the graph. The second one is the P matrix that has a diagonal. On its diagonal has the elements that correspond to the degrees of each node. And finally, the localization matrix is the difference between those two. The localization matrix has some neat properties. For example, it's a positive semi-definite matrix, and all of its eigenvalues are real and non-negative, which means that always at least one of the eigenvalues is equal to 0, and then the other ones can be sorted in descending order. So this second one, the second smallest value, is called algebraic connectivity or Fiedler value. And we will be using this as a measure of the connectivity of the network. So if this lambda 2 is equal to 0, then we say the graph is disconnected. Otherwise, the harder lambda, basically the harder connectivity. There are some exact expressions for calculating the lambda exact from the topology, but in most cases we have to rely on some expressions that model the upper and lower limits of lambda and need to calculate it exactly from the localization matrix. It has been shown that the speed of convergence of consensus protocol, which I'll talk about a bit later, depends on this value. So the harder lambda, we have the better performance of the system, but like I already mentioned, it also means higher energy consumption and possibility of delays. So our goal is to devise a system that will keep this lambda on desired level. In consensus, agents are only aware of their neighbors and thus unable to directly determine topology of the whole system. So the information needs to be propagated through the network somehow. We use the consensus protocol for this, and we started this simple discrete update law. So this is basically the elements of the adjacency matrix. And this first term is the communication link quantity between agents I and J perceived by agent L. This is the sampling interval, and then finally we have this term that we need to determine in a way that will ensure that each of the local estimates finally converge to a common value. We can start by using the general form of the trust-dense stasis, which we developed in our previous work. So we can see here that we have the state of the current agent. This could be temperature measurement, position, or anything else. We have a communicated state from the neighboring agents, and then we have a trust of agent I towards agent J. What we lack here is some kind of a measurement that we can measure by the system. So in our case, the quality is measured as a difference in the number of transmitted and received messages. But as you can see, it can differ between the directions of the agents. So we take the maximum value in order to ensure the graph remains undirected, simply because this whole graph grid is not connected to the lambda 2, is not very established for the directed graphs. Finally, we take this result and formalize it in a way of exponential function that is our observation function. So when we add this final measurement, actually it's a difference between the measurement and the current value. We add to the previous trust-based consensus. We get this final form that depends on the communication quality between two agents, the difference between our own and neighboring agent's opinion, and so this measurement difference. And this ensures the convergence of the values at the end. So the controlling of the algebraic connectivity is actually means just controlling the position and the number of links in the system. After we add a link in the graph, the lambda 2 will either increase or remain the same, and the opposite is true for removing one. So our basic workflow at each timestamp is to determine the local estimate of the adjacency matrix, calculate lambda 2, and then calculate the tracking error. So this is simply a reference minus the current value. And if this is larger than some dead zone, then we want to add a removal. So this dead zone is used because lambda 2 is not continuous in a way of links. So there may be some values that cannot be reached. So we use one of those expressions for upper and lower bounds and determine the minimum degree each node has to have in order to be able to achieve this reference value, which will be important later on. Then we use this modified Albert-Barabasi model. So this is a model that creates small growth networks. Those networks are fitting for modeling the multi-robot systems. And then the link creation and removal is dependent on some kind of probability. And this probability is calculated depending on the degrees of each node in the system. So in general, the nodes with higher degree have a better chance of getting new links because they contribute to the overall connectivity a bit more. And the opposite is true for removing a link because if you would do the same thing, then most of the newly created links would soon be disconnected again. We also run this protocol at frequency lower than the consensus protocol because we want to avoid frequent changes in the links. So we did some experiments with this. I will present two scenarios, one with the topology with 5 agents and the other one with 9 agents. We use this time sampling time of 0.2 seconds, dead zone of 0.1, and the connectivity control was running at each 25th cycle. So in the first experiment, we can see that our system is able to achieve consensus on the overall topology of the network, which is achieved somewhere around 20 seconds. And then at 50 seconds, we artificially lower the quality of the communication between agents 1 and 2. And you can see that the group as a whole quickly recognizes this difference, and the overall algebraic connectivity decreases. It is also interesting to see that agents 1 and 2, which can measure this link, have the quickest response, while the other ones lag behind a little bit as the information propagates through the network. In this topology with 9 agents, we demonstrate the ability to track the desired value of lambda. So we allow some initial time for agents to reach a consensus on the initial state, and then we activate the conductivity control, and you can see the responses are relatively quick with some oscillations, but that is normal because of the discontinuous nature of the one. Finally, we also have a simulation of what happens if one of the agents completely fails to communicate with others. So you can see here that at around 150 seconds from the start of the experiments, we simulate a complete failure of agent 5. The overall lambda connectivity drops sharply, but then other agents soon discover that this agent stopped communicating with everybody else, so they kick him out of the group and then reassemble the links to maintain the desired connectivity levels. So we did this same experiments using these aMussel robots. The real problem here, and the difference from the simulation, is that they use acoustic communication with limited bandwidth. So only one of the robots can communicate at a single time, and they have 5-second communication windows during which they exchange 7 bytes of data, which means that the 5x5 matrix needed to represent those 5 robots needs to be quantized with 5 bit values. So because of these longer communication periods, we had to increase the frequency of connectivity control and also increase the dead zone a little bit because of this quantization error. We also hope to perform some real-world experiments here at the pool. So this is also a good opportunity. If you have any other questions, you probably find me there and find out more. So as you can see in this first experiment, the results are very similar, except from this relatively large discrepancies in the reached consensus values. And this is the problem of the quantization levels. You can also see here that at some point, one of the links took a dip in the values, and that was because the communication is not perfect, so one of the messages got dropped, which in turn means the observation function returned a lower value for this quality, but that didn't affect the overall system. In terms of checking connectivity, the responses are a bit slower because of this communication duration, of course, but we can also see that it tracks the desired lambda very well. This may look a bit like the error is too much, but it is within the dead zone we specified. And finally, we also made the experiment with failing agent. So somewhere around here at 3,500 seconds, I took the aMussel robot and removed it from the room, so it wasn't able to communicate with others. It took some time for others to discover that the agent is missing. But as soon as that happened, the connectivity started to go again further. You can see that there are some overshoots, but this is consistent with the simulation as well. So in short, the system is able to estimate the initial topology, it is able to track the desired lambda reference, Then, of course, it is able to detect failed agents and reassemble the links in order to achieve the desired values. So that would be all for me. Thank you for your attention. I'll just put up the slide with references if anybody is interested. So, questions?
Any questions for Marko? Okay, I will open the discussion. So, in your experiment, you're using the acoustic sensors?
Acoustic communication, yes.
Acoustic communication, so it's a sequenced communication. It's not like everyone can communicate at the same time. So consensus is also, let's say, switching. It's sequenced, and it complicates the consensus. It's usually not converging to average. So did you kind of tackle that somehow? Because your results look very good.
Yeah, there are some differences in simulation and in real system. So I don't think, well, this is probably the best way to show it. So you can see that there are like these steps in the growth of the lump value. This is because, so like Tamara said, the agents can communicate only in sequence. So let's say we model these steps of K. It's actually, we consider it as one step only when all 5 agents communicate their messages, and then these messages are stored in some kind of buffer and then applied at the same time. So we don't have some time differences. But in order to ensure faster convergence, each of the agents runs the consensus locally with the last received values. So this is why there are these steps in the graph. So basically, during this time, the agents run local consensus, and then when new information comes, there is this big step up. There are also some other problems because of the acoustic communication and limited amount of data. We had to devise a special communication cycle for sharing current matrices, geodesy matrices, and information about new topology changes. So this is also kappa is 10 cases. So for 10 consensus cycles, there is one topology change cycle.
Thank you, Marko. Maybe another question.
I just want to ask a question about, did you take intermittent packet loss into your equation? When you move the agent out of the room, it stopped transmitting. But what if some particular packet fails? What happens with that, and do you take that into account?
Yes, great question. We did take this into account. So this is exactly this slide. So in each of these 10 cycles between the topology updates, we measure the amounts of received messages. So we know that between each of these cycles, we need to receive 10 messages. So this is always this transmitted portion of the equation. And we measure the received messages. So if one of the messages or more drops out, then this measurement function takes a lower value, and then this also reflects on the quality of the links in the adjacency matrix.
Okay, we can also accept questions from our online listeners. Okay, let's thank Marko for his talk. So Ivan Lončar is a researcher also at Babić, and he's doing his PhD under the supervision of Professor Mišković. Ivan also worked on subCULTron. We talked a lot about subCULTron in the last two presentations. So we worked on subCULTron, but also on Excelabust, Adriatic project and other projects. And his expertise is underwater acoustic localization. So today's talk is going to be on that topic. So even the floor is yours.
Hello, thank you, Tamara. Today I will be giving you a presentation about acoustic localization of underwater sensors using cooperative unmanned marine vessels. As you know, the underwater exploration and monitoring is an interesting topic in the last few decades. It has many applications, like in offshore industry, underwater biology, underwater monitoring, seismic event detection, and some others. And we want to tackle the problems of underwater monitoring, and there are several techniques that can be used. You can use basic probes and sensors which are manually deployed. They are simple, but you need to extract them to get your data, and it is tedious to have manual repositioning of the robots, and someone could even steal them if you leave them somewhere in the open. You can use also AUVs. They're more suitable for applications like bathymetry, but you can achieve monitoring through periodic missions. For example, you can inspect coral reef growth, so you can take months or years in monitoring that environment. You can even use drifters. There is one project which is called Argo, which made a worldwide sensor drifter network. Those drifters are carried by currents. They sink to some specific depth, and they get carried by currents. And during their mission, they're collecting data about currents, position, and they can even gather data for some speed profiles. And when they sync up, they send the data to the satellites to the operator, so you don't have to recollect. And the most interesting of these are sensor networks, and I will be talking a little bit about them. There is various types of sensor networks, some of which they can be moved, they can be placed in the bottom of the sea with cables attached to them without, so acoustically linked. They can even be mobile or etc. And for me, the most interesting ones are the acoustically connected sensors. These types of networks are mainly used for long-term monitoring, since deployment is it's expensive, so you want to have as much utilization from them as possible. One of the approaches, of course, subCULTron project. My colleague Anya and Marko talked a little bit about them, so I don't have to. But basically, I want to use surface vehicles and underwater sensors, aMussels, for the monitoring. And so here they are, as you've seen them. And basically, you have a system which can relocate, recharge, and deploy aMussels, and we want to use them for underwater monitoring, and we want to cover the area wider than the acoustic range, and of course achieve long-term missions. And the most important part is to georeference the acquired data we collect during the mission. So my research goal is to develop methods and algorithms for the localization of underwater sensor networks using USVs. And now I'll talk to you about subCULTron approach for localization. It is, of course, acoustic-based, since underwater agents are equipped with low-cost acoustic modems. ASVs are used as localization anchors. That means they're practically reference point with known positions. And we use time difference variable measurements since they're energy efficient. Since all surface agents are broadcasting the localization data, and they don't require any feedback from the underwater sensor, so then they don't waste unnecessary energy in broadcasting acoustic signal. And it offers simultaneous localization because underwater agents are listening passively and localize themselves. Here you can see one experiment where surface agents broadcasted acoustic messages and the underwater agents localize themselves. When they receive the triplet of acoustic measurements from the surface vehicles, and when they collect their data, they can localize themselves. And as you can see from this picture, the localized sensors have different uncertainties in the acquired positions. Can we determine that precision before the experiment or during the runtime, because we have no feedback from the underwater agents? And is it range dependent, since the aMussel in yellow, which is closer, has a lower uncertainty position than one in red and in blue. Here we have a map which represents some kind of sensitivity analysis. It's basically error propagation, uncertainty propagation from timing measurements to localized positions. And as we see, the area in red denotes the area where the agents are not uniquely localizable. Area in blue shows the area with lower uncertainty than that in yellow. And visually, we can see that the data correlates. The uncertainties in the position of the agents correlate with the uncertainty we get from the map. Now we want to localize our whole sensor network. And for that, we need, of course, multiple ping sets. I didn't define a ping set. Ping set is a triplet of time difference of variable measurement. So when all three agents ping, you can localize yourself. So what is the information shape we should use for the surface anchor, since they are mobile agents? What is the exact number of those ping sets or time difference of variable sets, and what are the locations of the pings? What should they be? And this is the example. In the left figure, we can see an area of interest. This is the area where our underwater agents are placed into the water, but we don't know their exact position. And if we do a ping set at this location, we will localize only this area with enough precision in a way. And the right figure shows in green the area which achieved desired precision, and the area in red shows the area where we didn't. And the darker the red, the closer we are to our threshold of the desired precision. But first, we need to find a way to combine those multiple maps. So we can expand our area if we ping from two different locations, but if we merge them, we can have better precision, since we see here that minimum value lower, so we have better precision here in the middle, but the area is not that larger. And now we come to the mission core, the whole mission where we want to localize our sensors. Of course, in the beginning, we define the area of interest where we place our robots, and then we need to, the interesting part is to choose the best anchor configuration, determining the necessary number of time difference arrival sets, and finding the anchor formation locations for achieving desired localization precision. Regarding the best ASV formation in literature, the best formation for the ASVs is regular polygon, basically a regular triangle in our case. But the baseline is not defined by that criteria, so we need to use some other criteria, and that criteria can be dependent on the range model used or some other stuff. Now we get to the question of number of time difference of arrival sets. How many sets is necessary to achieve desired localization? And because more pin sets require more time and waste more energy. Can we even determine the minimum, and what coverage percentage is enough? Because that also impacts our choice of anchor. And now we get to the finding the specific anchor formation locations, which is denoted in X. X is just showing the center of the formation, not to put 3 X's on one picture. And when we use one pin set, we have coverage area of 0.24%, which is quite low. But if you take 20 agents, we have greater coverage of 11%, which is more than 20 times better than the previous one. We placed the middles of the formations using F-min-con, simple minimization algorithm. We fixated n, here's n equal 1, and there's n equal 20. And the cost function is only the coverage percentage, because that is all we care about. And if we further increase the number of agents, here we have 65 agents, and we achieve more than 1% coverage per agent, as opposed to 0.24 when we just put one thing. And if we further increase to n equal 115, we almost cover the whole area, but there are some areas which are still not covered, and that's because the simple F-min-con algorithm fell into a local minimum, and we could probably find a solution which would achieve 100% coverage for this number. And if we increase the pin sets to 200, of course, we will cover the whole area, but at the expense of taking more time and wasting more energy. And this, I will show you a video if we have time. I will just play. This is an experiment we did in Beograd. This is the final results of the subCULTron project, where we show all the functionalities and the missions we wanted to show at the end of the project. And as Ina has stated, it is very difficult to work with a lot of robots in water, and that's why we use them in pools. Because it is relatively easy for them to drift apart if we are in open water, like we did in Laguna Plants. And with this, I will just leave the video, but I will conclude the presentation. With this, I will conclude the presentation, and you can ask the questions.
everyone is on time, or even finishes a bit earlier. There's a question, right?
I have a question regarding the position estimation, or better to say the position calculation. You use the time difference of arrival, so you get some, and I understood well, you get a few different distances, each distance corresponding to the anchor sensor distance. So it's a classical trilateration problem, right?
No, we get, since we don't, I didn't go into that much detail, but the surface vehicles are only broadcasting acoustic signals, and underwater agents are storing the local clock. They don't know when the signal was sent, but if we take into account that they received those acoustic signals at some points in time, and we know the difference between when the anchors broadcast those signals, we can get basically time difference of arrivals and differences in ranges between the multiple agencies, if I explained it well.
Yes, that's it. So the next step would be from these distances to calculate the agent position, right?
Yes.
And I'm interested in how do you do this?
I used, I don't have the exact formulas here, but there is an exact solution. If you have three time measurements and one depth measurement, you can use a projection technique that will limit it to basically a 2D case.
Mm-hmm.
And then from those three anchors, you can calculate the position. So I don't know if you were asking about maybe you thought that the three agents were weird, and you thought that you needed 4 for 3D case, but I think
we can take it offline when you want later, only to be much more precise. Independent of two-dimensional or three-dimensional calculation, you will have some nonlinear equations, and we work together with this. So
yes, you can ask me for details. You can ask later, and I will not bore everyone else.
Okay, we know it's a little bit tricky to solve, so I'm interested in the algorithm.
Yeah. Okay. We can.
Okay. Thanks.
Any more questions from the audience?
Thank you for the presentation. Have you tried with the 4 apex on the surface just in case you have an issue so for redundancy and you have a better baseline, or just with 3?
I've used 4 apex, but when solving the equation, I used 3 at a time. But now I'm looking into least squares methods, which use all 4s at the same time, but with time difference of arrival measurements, it's a little bit tricky because you don't just have 4 measurements, but you have 4, a lot of combinations. So if you have 10 measurements, the problem expands.
Probably also have more percent deviation.
Yes.
Okay.
Any more questions? I think you're okay with the time.
Okay, so just another short question. So what are your, let's say, future actions now? You mentioned that you want to kind of improve 4 apex into optimization.
And I used 4, and I can generate. I wanted to generate those maps and find solutions for all 3. But if I use 4, I can generate. I want to generate some kind of map, so I can use some easier methods of optimization for finding the positions I've shown, for example, here. Now I'm moving a little bit to the least squares methods because maybe that technique can offer me easier representations of the precision of localization for the underwater agents without any feedback from the underwater agents.
Okay, that sounds interesting. You can also continue your talk later. So thank you, Ivan.
Thank you.
Okay, we have one more lecture. But before I introduce the speaker, I will just announce the talks after lunch, happening after lunch. So at 2:30 we have actually one public defense of thesis topic by Marcela Polić, and she's going to give the area of applying artificial intelligence and soft robotics for agricultural robotics. So it's a bit different than this. So that's at 2:30. And then I think at 4:15 we have also one tutorial given by Julia Mach, who is going to talk about ROS2. So these are events after the lunch. And this last talk for this session is going to be given by Professor Ivana Palunko. Ivana Palunko is an associate professor at the University of Dubrovnik, and she is the head of LARIAT laboratory, which is a laboratory of intelligent autonomy systems in Dubrovnik. Ivana did her PhD in the United States in the University of New Mexico under the supervision of Professor Lončar, and later on she did her postdoc at Across Center in University of Zagreb and also in Technical University of Munich. Her interests are aerial vehicles, robust control, and many more. And today she is going to talk about adaptive optimal control in cooperative and decentralized systems.
Thank you, Tamara. Thank you, Tamara, for the introduction. Okay, thank you, Tamara, for the introduction. Let's first fix the PDF. Okay. It's a pleasure to be here. I've been here for a couple of times, and I know most of you, but I have to say that in the last couple of years, I haven't been around. There have been new faces around, so it's a pleasure to see that you guys are growing and to see familiar faces and the new ones. Okay, so as Tamara announced, I'll be talking today about the adaptive optimal control in cooperative and decentralized systems. But before that, I'll start by introducing us. So I moved to University of Dubrovnik in 2015. We are a young team, and the lab has been founded in December of 2019. We were only 3. By now, there is 7 of us, so 2 professors, 2 postdocs, 2 PhD students, 2 of them are here, and an engineer. In 15 days, we are getting 2 more members, so it will be 9 before we reach year 1, so which is good. That's thanks to all the projects. The 2019 was the first full year, so we started 4 new projects in 2020, and as a consequence, we are growing. So I think we are now complete to work for a new couple of years, something interesting. So hopefully in the, let's say, couple of years, let's say in 2023, we'll have interesting results as you guys have in subCULTron. Okay, one of the projects that we are involved with is in Mare, and tomorrow will be a roundtable around that project. So please join us and see what the plans are there. Okay, so in general, what we do, our research area is, so in nonlinear control and adaptive control. Why? So robotics in general moves from being just in the lab and being happy with moving the robot from point A to point B, and then stabilizing the system, doing some optimal control around the trajectories, because robotics is starting to move in everyday life. Moving in everyday life, and of course the end users have specific requirements. Your systems are not anymore familiar. You don't know the full system, and usually you're required to work in unstructured environments, and of course to work with other robots which are not necessarily of your type. So now we have heterogeneous systems, and of course cooperatively working with humans. Considering that, we have a lot of let's say problems that we encounter in general as scientists, how to deal with these issues where we have nonlinearities that appear from cooperation between different types of vehicles to communication in realistic communications, because in multi-agent systems we are all assuming that your communication is perfect, but there could be some dropouts or you have asynchronous communication, which is not trivial to solve. Therefore, since my PhD and later, we've been working on adaptive control based on learning and stability and robustness of controllers for multi-agent systems and cooperative systems. Okay. So applications are, as I said, heterogeneous cooperative systems or multi-agent. So regarding the equipment, we are growing, so we have more or less, we are mostly UAV, so drone guys, but since we are at the University of Dubrovnik, it is natural for us to move to marine environment because our university researchers are mostly oriented to marine applications. And we have some student projects which are cool just to implement stuff on. Regarding the infrastructure, so we are happy and lucky to be at our university because we have all the needed infrastructure. So for example, these Bistrin laboratories are just 20 kilometers away, and we have a concession, so we don't have extra permit. We don't need extra permits to do autonomous experiments with underwater vehicles, as opposed when you're going to older waters. And regarding the infrastructure, we have also 2 university ships that we can use, and we are very happy to go with our colleagues from Institute with them to do different kinds of applications for their research. So therefore, we get new ideas for research projects and collaboration. Okay, so that would be about us. So in general, cooperative decentralized systems. So if we okay, I thought PDF would be easy. Technical solution. Nećemo gledati video. Imamo bedali video u prezentaciji. Moraju se pruvati. Ok. Mogu li spojiti svoj laptop? Moraš aprovati u PDF-u da se može otvoriti video. Okay. Sorry for this. We had some technical difficulties.
PDF, kako to napraviti?
Okay. Okay. Can I connect my laptop? I mean, okay. Samo odobrenje za video.
Ne znam, sad na Teamsu se snima sve i šeramo.
sve ide. Pa samo vidi, ali mora probati u PDF-u. Ovaj PDF je što je?
Nema video. Ne, ne smije klik ništa. Šta možeš samo video prebaciti?
Ne mogu, embedani su u prezentaciju, mislim.
Da, stvarno nisam. Probat ću prebaciti.
Ne trebaš, nije ti sad do stika, nego do PDF-a, do readera. Ovo to stavim full screen.
Ne full screen, točno.
To, dopusti malo. To, ok.
Spoj negdje pa...
Ne može spojiti, sve u PDF. Mislim, izgleda kao u PDF, to bi trebalo biti najrobustnije.
Ne znam što mi ne da uopće da imam full screen.
A koliko je komplicirana sva pribar?
A snima se u Teamsu već sve i zvuk je spojen.
A vide i sa strane, baš da ih pokreneš sa strane?
Cijela motivacija, ali dobro. Ok.
Bravo. Ne znam što je. Imate mi. Zvaću te na kolo samo, može?
Ja nikad to ne to.
Možeš tim sam otvoriti.
Čekaj, ne spet. Piše ovdje, neka je šifra.
Možeš otvoriti Teams, pa ću te...
Imate Teams. I to...
Microsoft Teams.
Imaš neki online.
Ima, da. Ovdje na BTS.
Tehnička podpora.
Join to call.
Yeah, sorry for this. Most of the presentation is videos because if I don't shoot the videos, then we can go to lunch. So.
We have enough time also for presentation and also for lunch.
Okay.
And other effects.
Okay. I sad šeraš svoj screen. Ne, samo zašeraj, to će se pojaviti na gornjem screenu. Međutim, Teams, share.
Yes, your entire screen. Sorry, you check the application window. Yes.
Okay, sorry about the technical difficulties. I think we sorted things out. So I will let Ivana continue the presentation.
Okay, my PDF goes in full screen, so that's it. Okay. I'm not sure about it. Yeah. Okay. Okay. Sorry for the delay. Now we're fine. Okay, so regarding the cooperative decentralized systems, so let me first define what we consider cooperative and decentralized. So cooperative systems are any systems where you have multiple robots. For us, since we're in robotics, right? Systems are robots where you have some mission to accomplish, right? So either you can have one robot tracking another robot passively, or they can have a collaborative, let's say, approach where the goal is to land, or, for example, in this 2 videos, an old application where you have a UAV delivering something but around humans, so you have to ensure safety, or as in this application, this is an old work as well, you have a KUKA where with a human you have to do something collaboratively, or in some of the cases where human injects some interference. These systems have their own problems. Problem, of course, is in added nonlinearities and communication for controls. Okay. If we go to multi-agent systems, we all know that we can distinguish between centralized, where you have a group of robots which are controlled centralized from a central computer. There you have optimal trajectory generation and problems where you are not feel safe if your central unit fails down. In decentralized systems, each unit is, let's say, calculating its own control laws in a decentralized way with a common goal. One of the common applications are swarm birds, like we have the simulations here. Okay. Another application that we are interested in, so most of our research is focused on these cooperative, heterogeneous, and classical decentralized systems. But recently, since we started playing with these modular robotics, we'll look into this as well. These systems, so the trick with both types of these systems is that you know the general dynamics, but going into modeling all the interactions is tedious and not trivial. So how to approach these systems is to design a better control. What can happen, so for example, this is across, if you remember, this was done back in 2015, where we demonstrated that if you have a classical multi-agent systems with homogeneous, so basically you have 3 quadcopters and you have a stable system, stable controller, which is everything is proved and everything is perfect, just decreasing the communication channel, so the frequency, can destabilize the system. The same as with the suspended load. Usually the suspended load is always demonstrated on larger systems where the ratio between the suspended load and the load of the aircraft is relatively large. But if you have small systems where this ratio is lower, then basically two stable systems can destabilize each other if you don't augment the control system. Okay. Okay, so that's why we approached the notion of this adaptive optimal control. Because if you have a standard model of the system, you can approach it either if it's linear or non-linear, you can approach it from an optimal control perspective. So if it's linear, then you use some kind of LQR, which is stable and optimal, which is perfect. If it's non-linear system, then you somehow find a way how to either linearize it or to find a solver that will solve your somewhat piecewise linear, non-linear system. If everything is perfect and your dynamics doesn't change, then your performance is very good, as desirable. Since we are, as I said, we are dealing now with real life applications, it's so the change in dynamics is acceptable, something that we expect and that we have to somehow adapt to. So therefore, we have the adaptive optimal control, where the problem there is how to compute something that is adaptive and optimal at the same time. Is it stable or not, which is not a trivial thing to do. So how what we used for this is basically the reinforcement learning. So there is a paper from Sutton where basically reinforcement learning is a form of direct adaptive optimal control. It's been around for, let's say, last 10 years, but in the last 5 years, people have been extensively looking into how to prove some, let's say, performances for these algorithms. So basically, you have a controller, you have a process, and you have a reward function. So how to deal with that? This paper by Frank Lewis from 2009 outlines that policy iteration basically solves directly the adaptive control algorithm in an optimal way. You can use something else. This is just one of the applications and one of the ways how to do it. The trick here is, depending on what you're using, you can even use it without knowing the system's dynamics. So basically, if you have a deterministic Markov decision process, a reward function, and a controller that can be a function of the state and the return, then you can solve by accumulating Q the Bellman equation. So now the trick is how to solve this, because how to construct this optimal Q from which you can construct the controller is not a trivial way. And of course, if you don't know the system dynamics, so if you know it, and if it's linear, this boils down to the LQR, as is presented by one of the papers of Frank Lewis. If you don't know the F and H, then it's not a trivial problem. Then you have one of the variations is the policy iteration, where basically you have a greedy policy and you're solving the Bellman equation in every step, getting the maximum out of your value function. So in continuous spaces, we can approximate the Q, because if we don't know the system, the QF, you cannot construct exactly. If you don't know it, you can try to approximate it. Approximation can be done in many ways. Like most common is neural networks. Neural networks are well because they are absolute approximators, but they're not maybe as fast as some other approximators. So you have to be careful. So you can use here Gaussian processes or neural networks or polynomials or, for example, Chebyshev polynomials, whatever fits your application. Of course, it depends how long the choice of approximator, let's say, dictates how close you are to the real value function and how fast you converge. The better you approximate this Q, your controller will be closer to the optimal, right? If not, then you're off. And you you get a solution, but you cannot claim that it's optimal. So there is this, let's say, play between what you're using for approximating it and how to solve it. Okay. In our case, we use the Chebyshev polynomials. You can, because they're orthonormal and they have really good properties. For example, they're really fast in convergence. This algorithm I've implemented on a couple of systems, among others to UAVs with a suspended load, and this cooperative load manipulation with the KUKA arm. But here I want to show a new application that we came up with. So, if you have a multi-agent system, okay, sorry for this, okay. Okay, so if we have a decentralized control, so classical,
Sure.
okay, okay, I can be a tech support if you need. Okay. So if now consider a multi-agent system, a classical one. We all know the consensus algorithm and how it works. So the problem there is the data, if you consider, like, why do you want to exchange data all the time? Because you can reduce the energy and you can reduce the chance of being so-called security reasons. So if you model this system and consider these asynchronous intervals, you can get performance versus lifetime. If you're solving the local DP problem, then you'll get the non-stationary cost to go. The problem here is how to model if you set the system. So even if you have a linear system of homogeneous agents with a stable linear feedback, which is simple enough, then you have to model how this intermittent communication between the controller and the system looks like, and then you have to ensure that it's optimal by choosing it. So as you can think, it's pretty not straightforward. So that's why we use this algorithm to show that even not knowing the dynamics, we can get good behavior. So the standard equation for heterogeneous linear agents, where we added the disturbances, because we are modeling the realistic channel. So we have the noise, we have the delay, and we have asynchronous communication. So we have the common decentralized policy, and everybody knows, like, if you apply this to multi-agent systems with a certain, let's say, rules, the system is stable, right? But not necessarily. So we denote tau as a sample interval and the D as delay. This is a simple 4-agent system. If we put into the closed loop dynamics, it looks like this, where the standard A is diagonal, C is diagonal, and the other stuff is more or less straightforward. Here we are modeling the delay as well. And the omega is the noise. Okay? So if we put a performance index, minimizing the cost to go for the energy trade-offs, we get something like this. And now we have to solve it. For solving this, so basically for the least square policy iteration, instead of using a state of the UAV as a state, we are using the interval as a state. The trick with least square policy iteration, that we can, let's say, claim that it's suboptimal, but we cannot claim stability. So that's why, before doing this, we need to ensure stability. Based on small game theory, we have the upper bound on stability from 0 to some, let's say, frequency, and in between is somewhere an optimal frequency for each, depending on the performance of the system. Because if you're hovering, you don't need to communicate all the time. If you're doing an aggressive maneuver, you need to sample more frequently. So that's the goal of the whole motivation. So if we set this interval as a state, okay, then we can perform, again, the least square to get the optimal action. This boils down, so basically let's say, the good thing about least square policy iteration as opposed to the other Q learning techniques is that the nasty looking Q Bellman equation boils down to basically a couple of matrices and their inverse. So it's really fast. So we run this algorithm in real time while we were doing the experiment. So we started with, the linear system was identified just to get the upper bound, so the stability bound on the system, because we cannot claim that our system is stabilizable with this controller. We can claim that it's optimal. So we got these parameters. What we are using is crazy flights. So it's basically a simple linear system of the second order with a delay. Okay? The graph looks like this, nothing special, but please keep in mind that each of these lengths can be asynchronously sending the feedback and the sensing. So not, let's say, every second or tenth or whatever time, but they're all deciding by themselves how fast they should transmit the data. So each of these agents is running their own least square policy iteration based on the local information about the distances where they are, because the goal of this, let's say, multi-agent formation is to keep the formation following the lead UAV. We implemented this in real system. So basically each of them is running their own algorithm, and then let's say the chosen transmission interval changes depending on how fast they're going, or basically the performance as according to the formation needed. So they'll be doing, so I mean, just to keep you, these quadcopters are really small and fast and stable. So these lagging is because of the delay in the system. So you have a leader, and they are lagging because we have the real decentralized control with the real delay. The goal here is not to overcome the delay and have a good tracking, but to minimize the transmission interval between them in order to keep the formation stable. Okay? I'll show, just to show you the results, and then during the questions I'll let the video run. So basically the goal was to reach certain positions. These are the velocities, so everything was as expected. And the algorithm, so basically these are the coefficients of the Q function that we learned. So you can see that after a certain amount of time, it learned the whole function and they basically converged. And these are the transmission intervals. So basically for the leader, you can see that it's the maximum. So because the leader is looking at itself and it's not looking about what is happening with the others. So he doesn't need to communicate his own position that fast. The others, depending on the connectivity graph, they are transmitting either faster or slower. Okay. That's all for now. Thank you for listening. Questions?
Thank you for the presentation. I saw you have adaptation based on the speed of and the maneuver of one of the vehicles, right?
It's in all of it. It's
In all, yes, okay. Do you have adaptation if one link fails, like if one has a jamming problem or loses communication? Can you adapt dynamically the network?
We didn't, so no, on this application, so currently we were not considering that because that's a change in topology.
Sure. Exactly.
So we were adapting to the change in the transmission intervals. So the topology is fixed, but definitely the next step would be to see how it adapts to the change in topology. But there have been a lot of papers around about that.
Okay.
Do we have more questions? So what are your like scenarios? What kind of applications are you envisioning? Here you have this, it says swarm formation control. Do you have some other applications in mind?
Yeah, so for example, one of the, let's say, straightforward application would be platooning of the vehicles. So if you have a leader, you don't have to look at all the platoons all the time, and basically you can have this. And there's been a lot of extensive research in this asynchronous communication in this, and definitely underwater. So where communicating is really expensive, so basically you want to save every time that you're sending information. So for the UAVs is a different thing, right? But if you're underwater, even to send 2 bytes is very expensive. So you want to minimize this. So that would be another application for this. Okay?
Any other questions? Okay, then thank you, Ivana. We can conclude this session. Okay, we finished a bit earlier, but now we have lunch, and then we continue at 2:30 with, as I said, public defense, with public defense, Maritime.
Kriv. To mi se prvi put dogodilo da PDF ne radi.
Da se nije uopće htio full screenati.
Ovo je čudna verzija PDF-a na ovom.
Super, stvari radi. Imate tim, to je baš dobro.
Da, trudimo se.
Ovo bolje radili, tako kao nešto ovim malim.
Da, to smo radili prošle godine.
Autopće postoje zaštiti jer parcela mora prezentirati javni razgovor na Teams koji je određeno do studija.
Activity control, ali da, sad se može provući kroz reinforcement i to, ne.
Samo što je to bilo, znači mi smo baš htjeli nešto što se ne može baš modelirati. Jer kako ćeš ti